Today we are going to revisit our discussion of our sets of numbers that we talked about back in previous chapters. So thinking back to chapter 1, in section 1.4 we defined all of our different sets of numbers. So we talked about our natural numbers, our whole numbers, our integers, our rational numbers, our real numbers, and our irrational numbers. Up until now, in these last two chapters, chapter 2 and chapter 3, we were restricting our domain to our set of integers. In this chapter, our universal set, or our domain, is going to be the set of real numbers. So we're going to include different fractions and decimals and other types of numbers that we did not use in the previous two chapters. Thinking about our basic subset relationships of our Euler diagram, on the left side of our Euler diagram, we have our naturals, which are contained in our wholes, which are contained in our integers, which are contained in our rational numbers. Then we have our irrational numbers on the other side, and then we can put these all together to get our Euler diagram for our sets of numbers. So our first example is going to look similar to problems that we saw in previous chapters. So we're going to label and place the numbers following in the following set correctly in the Euler diagram. All right, so our smallest set is our natural numbers, which is our n. Then we add 0, we get our whole numbers, which is w. Then we add our negatives, we get our integers. Everything in these three circles, again, remember, do not contain fractions or decimals. Then we add our fractions and decimals and we get our rational numbers. Our rational numbers we use the letter Q to represent. Our irrational numbers are decimals that don't end and don't repeat. Those are our irrational numbers that are represented by the letter T. Right, then all together, right, this entire rectangle represents our real number system. Right, so looking at this list of numbers, we're asked to place these in the Euler diagram. So our first number is 3 over 2. 3 over 2 or 1.5 or 1.5 is an example of a rational number. So it's going to go outside of our circles and in that square on the left. 2 is a positive whole number. A positive whole number is a natural number. So that's going to go in our smallest circle in the middle. Negative 3 is a negative number that has no fraction or decimal parts. So that's going to go in our integer circle. 0 belongs in our whole number circle. Right, to get from natural numbers to whole numbers, we add 0 and then we add negative. So the only thing we're ever going to see in that W circle is a 0. And then on the right side on our irrational numbers is our square root of 2. Again, it's a decimal that never ends and never repeats. Okay, example 2 at the bottom of the page looks similar to examples that we saw back in section 1.4 as well. So we're just going to kind of review these a little bit in addition to talking about our other things. All right, so n intersect I. N intersect I, looking at our Euler diagram, we're going to use this picture kind of directly above here to help us. N is our small circle in the middle, I is our larger circle. If we take the intersection of those, we want what is in both. Right? Our intersection of those is going to be this smaller circle, which is n. Right? If we were to union these two sets, n and I, well, we take the larger circle, we take our larger set, so we get I. So when we are thinking about things that are subsets, our intersection is always our smaller set, our union is always our larger set. Right, now if we compare Q and T, right, Q and T, if we union them and put them all together, we get our real numbers. Because if we add our irrational and rational, a number is either or, it's not both. So we put these all together, we get our real numbers. Our intersection is going to be the empty set, right? Because our rational numbers and irrational numbers do not have anything in common. Excuse me. You're either on the left side of our Euler diagram or you're on the right side. It's impossible to be both. Thinking about our definition of complement. Our complement means not. So if a number is not irrational, then it is rational. So our irrational and rational numbers are complements of one another. All right, in this last one, this is another example that we looked at before. Right, looking at these, we're going to intersect n, our natural numbers, with this set where we all have expressions that have denominators of 2. If we go through and we look at these, 2 over 2, 4 over 2, 6 over 2, etc., would all be natural numbers. They would be equivalent to 1, 2, 3, so on and so forth. So our intersection are things that are in common in both. So in this case, we're just going to use our natural numbers because we have them over here, and those are these numbers that are over here underlined in this set on the right. We don't include our other ones that stay fractions or decimals that we're not able to turn into natural numbers, so our intersection is simply our natural numbers here. Back in previous chapters, we talked about a couple of other different definitions. We talked about the definition of the word dense, and we talked about whether or not sets were closed under an operation. In order for sets to be dense, that means that we could pick two numbers in our set, and between those two numbers we're able to find another number in our set. So our rational numbers and real numbers are going to be dense. Our natural numbers and whole numbers and integers are not dense because we can't find another natural number, whole number, or integer, for instance, between, say, the numbers 2 and 3. In section 2.1, we talked about the idea of closure. The idea of closure meant that if we applied the operation to an element in the set, that we always get another element of the set. So we're going to go through and just kind of review our different sets of numbers, review our descriptions, talk about whether or not they are dense, whether or not they are closed under different operations, and how we can connect these sets together. All right, so we're going to start with our descriptions. Right, so our description of our natural numbers. Right, natural numbers are also referred to as our counting numbers. Right, so numbers such as 1, 2, 3, so on and so forth. To go from our natural numbers to our whole numbers, well, the only thing we add is 0. So 0, 1, 2, 3, so on and so forth. Then we jump to our integers. Now we're going to include negatives. So I'm going to put the ellipsis or the dot, dot, dot at the beginning to show that these go infinitely in the negative direction. Right? -2, -1, 0, 1, and 2. Right, these first three sets we list in roster notation. Right? And so we can actually list out each individual element in our set. For our next few sets, we don't use our roster notation, we use set builder notation. So for our rationals, right, we're going to start with all x, the vertical line meaning such that x is an element of a over b, where a and b are integers, and b does not equal 0. So our rational numbers include fractions and decimals. It also includes everything that come in the previous sets, but here we're thinking about fractions or repeating or terminating decimals. Our irrational numbers are all x such that x is real but not rational. So it is a real number. We can put it inside our Euler diagram, but it belongs on the right. It is not rational. And our definition of real numbers, x such that x is represented by a point on a number line. Okay. And our real numbers include all of these previous sets. Right? So all of these other sets we can represent using little marks or dots or something on our number line. Right? Thinking about the word dense, if we go back up here, right? We're told that our rational numbers and real numbers are dense, and we are told that our natural numbers, whole numbers, and integers are not dense. Right? So if we're asked if a set is dense, for these first three sets, we're going to answer no. Again, if we pick two numbers at random, say the numbers 2 and 3, we cannot find another natural number, whole number, or integer between those two numbers, so they are not dense. Right? For these other three sets, they are going to be dense. Right? We can pick two fractions and find another fraction in between it. We could pick two real numbers and find another real number in between it. Right? Closure. Closure means that if we take two elements of the set and we apply an operation, that we get another element of that set back. Our natural numbers and whole numbers are closed under multiplication and addition only. Right? We add two natural numbers or we multiply two natural numbers or whole numbers, we get another natural number or whole number back. It doesn't work for subtraction and it does not work for division. Our integers are closed under addition, subtraction, and multiplication. So here we can add, subtract, or multiply with integers and we get another integer left. We don't necessarily use division because we could do division of integers and end up with fractions. Our rational numbers are closed under all four of our operations. So they're closed under addition, subtraction, multiplication, and division. Our irrational numbers are not closed under any operation because of different things with canceling and using numbers such as 0 and 1, which are not rational numbers. And our real numbers are closed under addition, subtraction, multiplication, and division. Again, if we were to take a real number, add, subtract, multiply, or divide it, we get another real number back. All right, as far as our basic set connections go, we want to think about our subset connections. Right? So to begin with, our natural numbers is our smallest set. So we're just going to start with that listed. Then if we work out, our natural numbers is a subset of our whole numbers. So we can enter that in our table. Then our natural numbers is a subset of our whole numbers, which is a subset of our integers. So we could add that to our next line in our integer row. Then we could say our natural numbers is a subset of our whole numbers, which is a subset of our integers, which is a subset of our rational numbers. That takes care of the entire left side of our Euler diagram. On the right side, we can only say that our irrational numbers are subsets of the real numbers. And then if we put it all together, we can say that our natural numbers are subsets of our whole numbers, which are subsets of our integers, subsets of our rational, which is subsets of our real, and our irrational is a separate subset of our real numbers. Right, so a lot of the stuff that is in this table we've talked about at various different points throughout the semester, but it's nice to just kind of condense all of this information into one spot. The last example that we're going to look at in this section, we're going to look at domains, and this is going to be kind of similar to a few homework questions that you're going to see. Right, so identify the domain of each problem situation. So in example A, the temperatures is reported on the sign in front of SSC. The sign does not report fractional numbers. Right, so thinking about this, we're thinking about temperature. Temperature could be positive, it could be negative, it could be 0. Right, so if we have numbers that are positive, negative, 0, but not fractions, that would be represented by the integers. So an appropriate domain for this particular problem would be the integers. All right, for B, the number of students in an algebra class on a given day. There are 25 students on the roster. Right? So we could start with the idea of whole numbers. Right? Whole numbers mean there could be 0 or a positive number of students in class. We don't want to use integers because it's impossible to have a negative number of students in class. We could get more specifically. Right, and say that the whole numbers from 0, 1, 2, all the way up through 25 are also our domain. So we could have two potential answers for this one, depending on how specific we wanted to get. Right. Area of circles. If we're thinking about circles, circles involve the Greek letter pi, right, which symbolizes our 3.14, so on and so forth, a decimal that never ends and never repeats. Right. So if we're thinking about the area of circles, we're thinking about pi. That is going to be included in the real numbers. We don't want just the irrational numbers because maybe the measure of our diameter isn't a nice integer. Right? So our area of circles, our best fitting domain would be real numbers. So as you're going through the last few homework problems in this section, look at the type of numbers that you could end up with in your set, and then from there use that to answer your question about the set of numbers that would be a good domain for your situation.